Hi everyone. In this video, we are going to see about enzyme kinetics. That is, how do we derive a Michaelis-Menten equation? Yes, that is what we are going to see now. Along with the alternatives for the Michaelis-Menten curve, that is the LineWeaver-Burke plot, Haynes-Wolff plot, and Eadie Hofstee plot. So how do you derive the Michaelis-Menten equation? So that's what we should understand. First of all, the enzymes react with substrate to form what? Enzyme substrate complex. Yes. And the enzyme substrate complex again breaks down to form the enzyme and the product. So the enzyme is left off, right? So enzyme is not used up in the reaction. So it acts as a biocatalyst. It's not used up in the reaction. So finally, the substrate becomes product with the help of the enzyme. And the main action of the enzyme is acting by lowering the activation energy of the overall reaction. So the first forward reaction, the enzyme and substrate forming the enzyme substrate complex, the forward reaction, the constant will be K1. And for the reverse reaction, it is a reversible reaction. Yes, so the enzyme and substrate forming the complex is a reversible reaction. Whereas enzyme substrate complex breaking down to enzymes and product is going to be nearly a irreversible reaction. Yes, so the reverse reaction is denoted by the constant K2, and the enzyme substrate to enzyme and product, that's denoted by the constant K3. Is it fine? So now, how do you plot this graph? So first of all, when I take a substrate concentration along x-axis and the velocity along the y-axis, is velocity along the y-axis. So as I increase the substrate concentration, the velocity of the reaction is also going to increase, and at a particular point it's going to get saturated. Yes, when all my enzymes are getting used up or getting saturated, even how much ever you increase the substrate concentration, the velocity of the reaction is not going to change, right? So this is what is the curve. So whenever you increase the velocity, whenever you increase the substrate concentration with the available amount of enzyme concentrations, the velocity is going to increase. But when all of the enzymes are getting saturated, then the curve will fall to a plateau wherein it will attain the where even after you increase the substrate concentration, the reaction is not going to get that much increased. Velocity is not going to increase that much increased. So, but when does the reaction attain a maximum velocity? Yes, so this point is when it reaches, you call it as the maximum velocity or the Vmax. When does it attain the maximum velocity? It attains the maximum velocity at at infinity concentration. So that is, you can't estimate it, is it not? So at a concentration infinity. So that's why we have alternatives for this Michaelis-Menten curve, which is the LineWeaver, Burke plot, and all the other curves, Haynes, Wolff, and Eadie's Hofstee, which we are going to see. Again, what you should understand here is the increase in substrate is increasing the velocity, is it not? So this is what is called as the first order kinetics. Yes, so this is what is the first order kinetics. So here, when you increase there is a linear increase in the velocity with increase in substrate concentration. So it is following the first order kinetics. Whereas at a particular point, it's falling to a plateau, is it not? So in this case, there is no linear relationship between the velocity and the substrate concentration. Here, the linear relationship is lost. So that's why you call here as a zero order kinetics. Yes, you call this as a zero order enzyme kinetics. So for the linear order, you can denote this line using a straight line equation. That is y is equal to mx plus c. Is it not? As a straight line equation. But here, when it falls to a plateau, how do you denote this plateau? Or a very small increase in velocity with the increase in substrate concentration. How do you denote that? For denoting that, what we need is what is called as the Michaelis-Menten equation. So for this only, we will need Michaelis-Menten equation. Is it fine? So now did you know the significance of this Michaelis-Menten equation? Yes. So next we'll see about how we will derive this Michaelis-Menten equation. So first there is something called as the equilibrium assumption. Yes, equilibrium assumption is nothing but the enzyme with the substrate in the forward reaction forms the enzyme substrate complex. Yes, it forms the enzyme substrate complex. And what's the constant that is involved here? It's the rate constant. His rate constant is nothing but K1 for the forward reaction, right? Now, at K2 for the reverse reaction. So K1 and K2 denotes the rate constants of the forward and the reverse reaction. So remember that. Now, at equilibrium, the forward reaction is going to be equal to the reverse reaction, is it not? At equilibrium, the forward reaction should be equal to reverse reaction. So, the forward reaction, which is K1 into enzyme concentration and substrate concentration, is equal to K2 into enzyme substrate complex. Is it fine? Now, if I take a ratio of K2 to K1, what will I get? I get K2 by K1, sorry, ratio of K2 by K1, then what it is? Enzyme into substrate by enzyme substrate complex. Is it not? So K2 by K1 is nothing but called as the dissociation constant or the equilibrium constant. So as the session is going on, take a pen and a paper and work it out along with me, then only you will understand. Okay, so that's how I learned. So dissociation constant, or you will also call it as equilibrium constant. Understood? So this kind of reaction where we study that enzyme substrate gives enzyme substrate complex with a forward and reverse reaction, because it's a reversible reaction. So if we derive this kind of a dissociation constant, it's equilibrium assumption. Now we have another called as the steady state or pseudo steady state assumption. Okay, and that's also called as the Briggs-Haldane assumption or the pseudo steady state assumption. Yes, pseudo steady state assumption or hypothesis. Okay, so here what you should understand is pseudo steady state hypothesis. What we saw earlier, enzyme plus substrate, forward reaction, rate constant being K1, enzyme substrate complex. Reverse reaction is K2. And this enzyme substrate complex breakdown is what is going to give us enzyme and product. Okay, enzyme and product. Here again, in some books, they say that enzyme plus product is a reversible reaction that also can form enzyme substrate complex, but it's a very, very, very slow process. So we are not taking that into account. Okay, so we are not using that. So we are assuming that that kind of a reverse reaction is not happening. Okay, so enzyme and substrate. Also, one more assumption that we make in this Michaelis-Menten equation derivation is that the enzyme substrate complex concentration is going to be unchanged throughout the reaction. Okay, so that's how we are assuming. Now, enzyme substrate complex formation is equal to enzyme substrate complex breakdown. Okay, this is what happens at equilibrium. So we saw forward reaction is equal to reverse reaction at equilibrium, is it not? Likewise, enzyme substrate complex formation is equal to enzyme substrate complex breakdown in case of equilibrium. Okay, now what is enzyme substrate complex formation? Again, K1 into enzyme into substrate. That is what is enzyme substrate complex formation. What is enzyme substrate complex breakdown? Breakdown will involve two things. Yes, either this will break down into the enzyme and product, or this can break down into enzyme and substrate. Is it not? By reverse reaction. So we have two reactions here. So what can I write? I can write it includes K1 into enzyme substrate plus K3 into enzyme and product. Is it clear? Now, when I rearrange this equation, what should I get? What should I get? I will take this enzyme substrate outside. Or did I make a mistake? Yes. So here, again, this is K2, right? K2 into enzyme substrate. And K3 into enzyme substrate. All right. So let me just repeat it again. So enzyme substrate complex formation is equal to enzyme substrate complex formation is equal to enzyme substrate complex breakdown. Now, what is this reaction of? For formation, it's the forward reaction. So enzyme plus substrate into rate constant, which is equal to rate constant K2 into enzyme substrate complex or rate constant K3 into enzyme substrate complex. Is it clear? So this is how you have to break it down. Okay. So either for breakdown, either my enzyme substrate complex can break down into products and enzyme or substrate and enzyme. Okay. So I'm going to include on the rate constant K2 and K3 here. So just to understand this way. Now I'm going to rearrange the equation. What will I get? K2 plus K3 into enzyme substrate. So enzyme substrate complex, I can take it outside the equation. Now what will we get? K2 plus K3 divided by K1 is equal to enzyme concentration, substrate concentration by enzyme substrate complex formation. So what is this constant now? This constant is what is now called as the Km, which is the Michaelis-Menten constant. Is it clear? Which is the Michaelis-Menten constant. Understood. Yes, so this is what is Km. So now we have derived the Michaelis-Menten constant. Now, how do we derive the Michaelis-Menten equation? Okay, now Km we know. Now, what is this velocity V0? Velocity is nothing but the rate of change of product per unit time. Is it not? What is the velocity or the speed? So, rate of change of product per unit time. That is how much the enzyme substrate complex is going to break down into enzyme and product with a rate constant K3. Is it fine? So that's how it is, right? So what is this? How can you understand this? This is nothing but the breakdown of enzyme substrate complex. Is it fine? Now V0 is nothing but K3 into enzyme substrate complex. Yes, so we have this equation, right? We have this equation. So how this enzyme substrate complex is going to break down into enzyme and product with the rate constant K3. That is what is called as the V0, which is the velocity, which is nothing but the rate of change of product per unit time. So V0, I can write it as K3 and enzyme substrate complex. So this is one equation that we will remember. Okay. Now, what is the total enzyme concentration? So some enzymes can be free in the reaction or some enzymes can be bound with the substrate to form enzyme substrate complex. Is it not? So total enzyme should be equal to the free enzyme plus the bound enzyme. Yes, do you agree? Free enzyme plus bound enzyme. So total enzyme E0 is equal to, I will write it as free enzyme is just E and bound enzyme is ES. Okay. Now, this is one more equation that we need to remember. So, this is second equation. Now, when all my enzymes are bound to the substrate, that's how my reaction is taking place, no? So when all the enzymes are bound to the substrate, which means that all the enzymes are saturated. Yes, let me write it. When all enzymes are bound to substrate, then the free enzymes should be equal to 0, is it not? Free enzyme concentration will be 0. Everything is bound to the substrate, so it is in the form of an enzyme substrate complex. Yes, so at this point, the velocity will reach Vmax. At this point, the velocity reaches Vmax. Yes, so how can I write this equation? Vmax is equal to K3 into E0, right? K3 into E0. So when E becomes 0, what happens to the second equation? E0 becomes Es. Is it not? What happens to this equation? This equation becomes E is equal to Es. Yes. So I can rearrange this first equation to this equation by getting by understanding what is Vmax. So when all my enzymes are bound to the substrate, the enzymes are saturated. So the free enzymes are 0. Free enzyme concentration is 0. So my E is equal to 0. So E0 will be equal to Es in this case. So when E is equal to 0, when free enzymes are equal to 0, then the reaction has achieved Vmax. So Vmax will be equal to K3 into E0. Is it fine? It's just rearranging the equation that you get this kind of an equation. So this becomes the third equation for us to remember. Is it fine? So now what we are going to do is we are going to rearrange. Again, we are going to rearrange this equation. So how will you rearrange? What is E here? Okay. What is E? So let me rearrange the equation 2. So this is why I'm telling I can't swipe back and forth, right? So you have to take a paper and a pen, write it down, work it down with me. Okay, work it out with me. So when I rearrange E, second equation, E becomes E0 minus ES. Okay, E becomes E0 minus ES. Is it not E0 minus ES? Now, coming back to the Km equation. What is the Km equation that we have got here? Yes, what is the Km equation here? Km is equal to ES divided by enzyme substrate complex. Yes, so let me write it here. Km is equal to E into S divided by enzyme substrate complex. Now, can I substitute this E value here in this E value? Yes. So I will substitute. I will get E0 minus ES into substrate concentration divided by enzyme substrate complex. Fine. Now, let's just rearrange this. So E0 into substrate minus ES into substrate divided by enzyme substrate complex. Fine. Yes, again, let us rearrange this. What will we get? E0 into substrate divided by enzyme substrate complex minus enzyme substrate complex into S divided by enzyme substrate complex. Now, can we cancel these two? Yes, we can, right? So now what do we get? Km is equal to E0 into S divided by enzyme substrate minus substrate concentration. Is it fine? So I have got this kind of an equation. Now take this third equation. Yes, now take this third equation. That is Vmax is equal to K3 into E0. So what is E0 from this equation? So let me rearrange the third equation whereby I get E0, which is Vmax divided by K3. Okay. Now I will substitute this E0 here. Where? Here. Okay, I will substitute E0 in this equation. Okay, let's just name this equation to be 4. So now substitute in equation 4. So what do we get? Km is equal to Vmax by K3 into substrate by enzyme substrate minus substrate. Is it fine? So in place of this E0, I'm substituting. Clear? In the place of E0, I'm substituting Vmax by K3. That's it. Now what do we get? Again, now what do we get here? I know what is V0. Yes, what is V0? V0 here is by equation 1, I know V0 is K3 into enzyme substrate. Yes, so here again we will substitute equation 1 in the above equation. So what do you get here? Km will be equal to Vmax into S divided by V0, because we know V0 is what is K3 into enzyme substrate complex. Clear? Minus substrate concentration. Okay, now we are going to rearrange this here and there. So that let me just write it here only. Km plus S. So I'm just bringing the S this side. So I will get Vmax into S divided by V0. Now what is V0? Vmax into substrate by Km plus substrate. So have you seen this equation anywhere? Yes, this is what is the Michaelis-Menten equation. So we have come to this point. Okay, so this is what is the Michaelis-Menten equation that we have come to. Yes, we are happy. Yes, still we have lots to go. This is how we derive the Michaelis-Menten equation. Okay, let's just quickly recap what we had learned so far. So we will start from this point about according to this pseudo-state steady state hypothesis. We know there is this enzyme substrate complex which is formed. So we are assuming that this enzyme substrate complex concentration is constant throughout my reaction. Forward reaction rate constant is K1. Reverse reaction rate constant is K2. And this complex getting converted to enzyme and product, the rate constant is going to be K3. Fine. So at equilibrium, enzyme substrate complex formation should be equal to this breakdown. So enzyme substrate breakdown involves this rate constant K2 and also rate constant K3. So I will include both this. Yes, so the rearrangement of these constants, I get K2 plus K3 by K1, which is what is called as the Michaelis-Menten constant. Clear? This is the Michaelis-Menten constant. Now, what is the velocity? So ultimately, we need to find out what is the velocity. So what is velocity? Velocity is nothing but the rate of change of product, rate of conversion of this, the formation of the product per unit time, which is again nothing but the breakdown of this enzyme substrate. So V0 will be equal to K3 into enzyme substrate. K3 is what is the rate constant that's converting the enzyme substrate complex to enzymes and products. So that is what is V0. So let us understand this, remember this equation as one. What is total enzyme concentration? Free enzyme plus the bound enzyme. Again, when all the enzymes are getting saturated, what I will get is the E0 enzyme concentration will be equal to bound enzymes. Now, what at this stage, it will attain the maximum velocity. When all my enzymes are saturated, it is maximum velocity only, right? So Vmax will be equal to, when I substitute this equation here, I will get Vmax as K3 into E0. Clear? Now, what is free enzyme concentration? I will calculate. In Km equation, I will substitute. So I will get a Km equation. Now, with this Km equation, I will rearrange E0. I will find out what is E0. I will again substitute this Km. So whatever equations 1, 2, 3 that we have got, we're just rearranging, substituting in the Km equation. Okay. So finally, we get the Km equation. Again, you rearrange this and you get what is the velocity here. So V0 will be Vmax into substrate concentration divided by Km plus substrate concentration. This is what is the Michaelis-Menten equation. Is it clear? So now let's just understand two scenarios here. So when the substrate concentration is so much more than the Km, when substrate concentration is too much than the Km, then you can ignore the Km levels here, is it not? So let me again write this Michaelis-Menten equation, which is V0 is Vmax into S divided by Km plus S, right? So when my Km levels is very, very less, okay, and substrate concentration is only very, very high concentration, then I can just ignore this Km, is it not? So I will ignore this Km and what I will get is Vmax into S divided by S. Yes, so these two gets cancelled. So V0 is equal to Vmax. Okay, so what is this Km? I mean, when the substrate concentration is too much higher, then that has reached the maximum velocity. So that's what is the concept here. So when do you attain maximum velocity? When your substrate concentration, when the Km has reached its when the substrate concentration is too high. Okay, so that's when you have attained the maximum velocity. Now, second scenario is that when V0 is equal to Vmax divided by 2. So when velocity is half the maximal velocity, then how do you substitute here? I can substitute it here again in the Michaelis-Menten equation. So what is V0? Vmax by 2, okay, which is equal to Vmax into substrate divided by Km plus substrate. Okay, now I can cancel these two. So what do we get again? Km plus S, which is equal to 2 into substrate concentration. So Km is equal to 2 into substrate minus substrate. So which is what is substrate concentration. Okay, so what is Km here? Km is the substrate concentration at half maximal velocity. Now do you understand what is Km? Km is the substrate concentration at half maximal velocity. So these are the two scenarios that you need to understand. And you have to apply it in this Michaelis-Menten equation to understand what is Vmax and what is Km. So Vmax is the maximal velocity which is maximal velocity attained when all your enzymes concentration have been, when the free enzyme concentration is 0. Okay, when free enzyme concentration is 0 and substrate concentration is very high. What is Km? Km is the substrate concentration at half maximal velocity. So this is what you have to understand. Okay. So in the Michaelis-Menten graph, what did you find was that the substrate X is the substrate concentration, Y is the velocity. Yes, Y is the velocity. But the equation goes like this, but when does it attain the maximum velocity? That we don't know. Yes, that's a very tedious process. You need to keep adding more and more substrate concentration. So even infinity, right? So you need to wait till the infinity concentration so to attain the maximum velocity, so which is not practically possible. Yes, so that is why we have alternatives for this to understand or to calculate the Km and the Vmax. So those alternatives are what are the LineWeaver Burke plots and other two plots that we will see. So first we will see about the LineWeaver. First we will see about the LineWeaver Burke plot. So LineWeaver Burke plot is nothing but it's called as the reciprocal plot. Okay, it's nothing but called as the reciprocal plot. So consider this Michaelis-Menten equation. What is it? V0 is equal to Vmax into S divided by Km plus S. So I will take reciprocal of all these. So I will get 1 by V0 is equal to Km plus S divided by Vmax into S. So let us rearrange this. So Km by Vmax into S plus substrate by Vmax into S substrate. Okay. So I will cancel this. So I can write this equation similar to y is equal to mx plus c. So here y will be equal to 1 by V0 and m will be equal to Km by Vmax. X will be equal to 1 by S and C will be equal to 1 by Vmax. Okay. Now I will plot a graph. Let me plot a graph here. Yes, so I will have 1 by substrate along x-axis, 1 by V along y-axis, or 1 by V or 1 by V0 along the y-axis. So what is the x-intercept and what is the y-intercept you should know. What is the slope here? Slope is going to be the Km by Vmax, right? Slope is going to be the Km by Vmax. Yes. What is the y-intercept? What is the x-intercept? So how do you find out that? To find out y-intercept, you must substitute x is equal to 0 in the equation. Yes. So you will get y as 1 by Vmax. Okay, in this equation, if you substitute x is equal to 0, you will get y as 1 by Vmax. Now, if to find out x-intercept, then you have to substitute y as 0. Yes. So if you substitute y as 0, just if you want, just in case you want to do y as 0, this is 0. Yes, this becomes 0. So you need to rearrange the equation. So what will you get? What will you get? Km by Vmax into substrate will be minus 1 by Vmax, right? Or minus Km by Vmax is 1 by Vmax. So what will be the x here? It will be 1 by Km. The Vmax and Vmax will get cancelled. You will get 1 by Km. Is it fine or should I derive that? It's nothing but how does the equation go? 0 is equal to Km by Vmax into S plus 1 by Vmax. Okay. Now I'm going to bring this minus Km Vmax into 1 by S is equal to 1 by Vmax. Yes. So we want 1 by S. Yes. So 1 by S, if you want, then you have to cancel this. So if you want 1 by S, which is minus 1 by Km. Okay. So this is the X. So x-intercept is going to be minus 1 by Km. So that's how you derive this y-intercept also. So x-intercept will be minus 1 by Km. So here it is minus 1 by Km. Is it clear, all of you? So here is the y-intercept, here is the x-intercept, here is the slope, here is the x, here is the y. So this is what is the reciprocal plot or the LineWeaver Burke plot. Fine. So the next plot that we will see is the next. So here in this LineWeaver Burke plot, if you say x is 1 by substrate concentration. So when in too much of lesser, minute 1 by substrate concentration, it's very difficult to plot, it seems. So that's why they have brought some other alternatives also. That is what is the Haynes-Wolff plot. Okay, that's what is the Haynes-Wolff plot. Right. So here again, let me write this Michaelis-Menten equation. V0 is equal to Vmax into S divided by Km plus S. Okay, now I will take the reciprocal of this. So Km plus substrate concentration into V divided by Vmax into substrate concentration. Now what will I do? I will just rearrange this. So Km by Vmax into substrate concentration plus substrate concentration divided by Vmax into substrate concentration. So we will cancel the substrate concentration here. Now I will multiply the entire equation with substrate concentration. So what will I get? Substrate concentration by V0 is equal to substrate concentration Km by Vmax into substrate concentration plus substrate concentration divided by Vmax. Now we can cancel these two. Yes. So now what do you get? Now what have you got here? I will just rearrange this also so that we get S by V0 is S by V max plus Km by V max. Is it fine? Same thing only. Km by V max plus S by V max we've got here. So I will yes, we've got it here. I've just written as I'm just interchanging these two places only. Okay. Now this looks like y is equal to mx plus c for me. So y is equal to S by V0. So what is along y-axis? S by V0 along y-axis. Okay. Now x is equal to S for me. So x is substrate concentration, right? M is the 1 by V max for me. So in the equation, the slope is going to be 1 by V max, right? C is Km by V max. Okay, C is Km by V max here. And this is the intercept, right? So now this is going to be Km by V max. Y-intercept is going to be Km by V max here. So again, how do you find out this y-intercept, x-intercept? We know, right? So x-intercept, if you want to find, substitute y is equal to 0. So y if it is 0, then what you will get? What you will get? Minus km, is it not? These two will get cancelled, becomes negative. So you get minus km as the x-intercept. So the x-intercept is going to be minus km for me. Clear? Again, y-intercept, if you want to find out, then x is equal to 0. So sit and substitute x is equal to 0 and see. Only then you will understand. Okay. So x is equal to 0. Then what will we get here? Again, I have substituted x as 0 here. So I should get y is equal to km by V max. Is it not? Km by V max. So this is how it is. So this is what is the graph of Haynes-Wolff plot. Clear? Now let's move on to the next plot, which is the Eadie Hofstee plot. Eadie Hofstee plot. Now, again, writing the Michaelis-Menten equation, starting off with that, V0 is V max into S divided by Km plus S. Now, taking reciprocal of this, 1 by V0 is Km plus S divided by V max into S. I will multiply the entire equation with V max. So I will get V max divided by V0, which is equal to V max into Km plus S divided by V max into S. So I will cancel this V max. Okay. Now we'll take this V0 that side. So V max is equal to V0 into Km plus S divided by S. Okay. Now let us again open up the equation. Let me open up the equation. I get V max is equal to V0 Km. V0 Km plus V0 S. Yes, so we will cancel these two. So now I have got my equation. Now I will just do some rearrangements by putting V0 on one side. So if I put V0 on one side, I will get minus Km V0 by S plus V max. Okay. That is V0 on one side I will put. So you will have to take this V0 out. Okay, you have to just close the equation like V0 into Km, V0 into Km by S plus V0 is what you have got. So you want to bring the V0 to one side, this V0. Okay, this V0, you leave it on one side and move the V0 Km by divided by substrate to the other side. So you will get minus sign for it plus Vmax. So this is what is the equation. So now this is what is my Y is equal to Mx plus C. Okay, now here Y is equal to V0. X is equal to V0 by S. Okay, M is equal to minus Km and C is equal to Vmax. So now I will plot the graph. I get V0 by S for x-axis and along y-axis I plot V0 and I will get a line like this. So my slope is going to be minus Km, right? And the y-intercept is going to be Vmax. Is it fine? So this is how my Eadie Hofstee plot is going to look like. Okay, Eadie Hofstee plot is going to look like. Clear all of you? So this is how we derive Michaelis-Menten equation. So along with that, we have also derived LineWeaver Burke plot, Haynes Wolff and Eadie Hofstee plot. These two are alternatives. LineWeaver Burke plot you are expected to know. But in the recent paper, I had seen derive the alternatives for the Michaelis-Menten curve. That's what is the question was. So in that case, you have to know about all these three alternative curves, how to derive and plot them also. Okay. Yes. So now I guess it is easy, but you have to just keep practicing yourself. Just attend the session with paper and a pen, that will do. Okay, or just watch it once more in 1.5x. You are sorted. Okay, so thank you.